Hopefully you'll remember from my first video for this module that we mentioned that rates for reactions are always instantaneous because the concentrations are always changing. As soon as that reaction starts, the concentrations of your reactants are going to go down, the concentrations of your products are going to start to go up. And so if you look at the rate equation, as the concentration goes down, what happens to the rate? So if I just have my generic rate equation where rate equals the rate constant times concentration of reactant A raised to a power times the concentration of reactant B raised to a power. If I take these guys and I decrease them, what's going to happen to the reaction rate? Well, if this goes down, then this is going to have to go down too. So the further along you get in the reaction, the slower and the slower and the slower it's going to go. And so this is another really good illustration of why we said earlier in the year, reactions never truly go to completion because the rate just slows down and slows down and slows down and slows down. It's like it never quite finishes up. If I look at a graph of the concentration of the reactant over time, what you're commonly going to see is a graph that looks like this, okay? Now, if you want to find the slope of a line, remember from algebra, how do you find the slope of a line? Well, the slope of a line is the change in y over the change in x, right? Okay, so what is it for this one? Well, for here, the slope is going to be the change in the reactant over the change in time. Well, what is the change in reactant over time? If you remember, we defined that at the beginning of this chapter. The change in reactant over time is the rate, okay? That is the rate. So if I take the slope of this graph if you remember, again, from algebra, you're drawing a tangent line to that. That was supposed to touch. If you draw a tangent line to that slope right here, you're going to get a rate. If I draw a tangent line here, the slope of that line is going to be the rate. If I draw a tangent line here, the slope of this line will be the rate at this point in time. Well, what's happening to every single one of those? Well, to every single one of them, as the line goes from being very highly vertical to much more horizontal in nature, you can see that the rate, that it's going to go down because you've got a very big number divided by a very small number. And here you've got a small number divided by a big number. So it starts out big, gets smaller and smaller and smaller as you go along. When you get to the halfway point, where the concentration is exactly half of what it was before, then that particular point in time is called the half-life of the reaction. So basically, the half-life of a reaction is the time it takes for the concentration to be cut in half. You may have talked about this I know that in the physical science class that I teach, we talked about a little bit of nuclear chemistry, and we talked about half-life of reactions there. If you have not covered it before, I don't think you're going to find it difficult, and we're going to hit it a lot more when we hit the chapter on nuclear chemistry. So let's go through example 11.2. Again, this is not something that is going to be very difficult at all, but I'll show you how I set these up so that because there's some very common mistakes that I see students make when they're working half-life problems. So example 11.2 is on page 340. A decomposition reaction has a half-life of 5 minutes. So normally the way we write half-life is like this. Half-life, half of the time, half-life is 5 minutes. Okay. The initial concentration of the reactant is 2 molar. Okay. 2 molar. And I want to know what the concentration of the reactant is after 15 minutes. 15 minutes, what is the concentration? Okay. very common mistakes that I see happen. First common mistake is that, well, if the half-life is 5 minutes, then that means half of it disappears after 5 minutes, and then at 10 minutes, it must all be gone, right? No, half of it's going to disappear again. And so after 5 minutes, half of it disappears. And after another 5 minutes, another half of what's left disappears. And after another 5 minutes, another half of what has been left disappears again. And so it's not 2 half-lives and the whole thing is gone. Very common mistake that I see students make. So let's think about it this way. Here's my time and here's my concentration. At time 0, before this decomposition starts happening, the concentration is 2 molar, okay? Because that's what it told us. After 1 half-life, after 5 minutes, that means this concentration is 1 because I got half of what I had before. After another 5 minutes or after 10 minutes, the concentration gets cut in half again. So now I have 0.5. After another 5 minutes, the concentration gets cut in half again. So now I'm going from 0.5 to 0.25. Okay? So after 15 minutes, the concentration is 0.25 molar. So here's my answer right here, 0.25 molar. Now I told you that there were 2 very common mistakes that I saw. The first mistake is that assuming that half of it disappears in the first 5 minutes and the other half disappears in the next 5 minutes, which isn't true. It's half disappears each time. The other mistake that I see students make is they start out with 5 minutes up here at the top instead of starting out at 0. And so you need to make sure that you always start your time clock at 0 and not 5 minutes in, because at 5 minutes in, your concentration's not 2. It was concentration of 2 before the reaction ever started. So make sure that you don't make that mistake either. Okay. So here again, we see that it keeps cutting in half and in half and in half and in half and in half. And so again, it's very difficult to say that any reaction ever goes to completion unless, you get down to literal atoms that are left or literal molecules that are left. All right. So that is half-life, and we'll take that another step the next time.